Doğru. Okay. So in the previous week we have talked about the imaginary component in the math, right? What's the meaning of the J? Just remember me. Just tell me. What's the J? What's the meaning of this? Can you remember? Okay, J is the what is the dynamic component. For the basis of the what, the any signal in the universe, right? Just see that we have the signal just like this one. And so we have this sinus or cosinus components in here, and so we have the Pythagorean theorem just like this one, right? We have this nomination, and then we can write it this integral form in here with the values of the what, these terms. The square form dt must be equal to the 0 because delta s must be equal to the 0, right? Because if we have the any change in the hypotenuse, and then we can say that we don't have the any energy conversion or the energy change, right? And so if this is the case, and then we can create the dynamic system, okay? Because we return to the same point at each time, at every step, at every period, right? This is the proof of the what? The J. And so the J is the basis vector for the what? Dynamicity, right? Just see that. And so, and also just remember that we have the what? The infinite roots in here, just like this one. What's the meaning of the infinite roots in here? Anyone knows that? Huh? Yes. This is, or this can be considered as the frequency in the time domain, okay? And so just see the x, x1, x, x2, x, x3, and goes on to what? The x, x minus n is equal to the 0 for the what? For this signal, okay? And so this is how we can handle this dynamic form in the form of the what? The one coefficients. And so in order to write this term, or the instead of using this form, and then we can just use the J. And so we can create the what? The real and imaginary axis with the right angle, right? What's the meaning of this right angle? Yes, this creates the orthogonality, right? And so we can define the independent features based on this one, right, Ayça? You understand that? This notion, okay? And so if we are using this notion, and then we can just use the 1J in order to represent the what? The infinite roots. In order to what? In order to build our dynamic system based on the what? The time, or x, or y, or z, which is dependent of the what? The r definition, okay? But the time is a physical identity, or the events, and so we can suffer all the time in the universe, okay? And so we can relate this notion with the what? With the time, okay? This the J is utilized for the what? For representing the time roots instead of using these n-dimensional roots equations, okay? And so in this week we will continue with the what? The analysis of the what? The Taylor series, okay? What is Taylor series? Anyone knows that? Why do we use this Taylor? sum of infinite for the what? Any function, right? But how can we handle this function based on the Taylor series? Just remember that. Yes, but with what? We can define the function or the signal in terms of the what? In terms of the x squared, x over 3, x over 4, and blah blah blah, x over n components, right? And so we can define this function as an infinite roots in terms of the what? In terms of the x or its related coefficients in this domain, right? And so the Taylor series can be assigned with the what? This is the representation of infinite roots. In this case, series for any function, right? And so we have a beautiful formula for the identical form, just like this one. Mathematical notion coming from the what? It's the basis. Notion is given by this one. If you have the any data or variable, and then we can define this function as an infinite roots or the infinite over term, just like this one. Okay, we can model anything in the universe, because what is the reason to model the everything? How can this form model everything in the math? Because yes, they have the infinite roots, and so if we have the infinite roots, and now we can model the everything. Just remember that we have the Fourier series, right? Have you used it? Yes, right? And so how can we define any signal based on the Fourier series? Because we have the infinite components based on the what? The frequency or the J domain, okay? Or the imaginary domain. And so with the same idea, we can define any other function based on these nominations, right? And so if this function goes to infinity, just like this one, and then we can model anything. This is the results of the what? This function, okay? Because the roots are everything, and so roots are independent from each other, and roots are creating to what? The another or the independent axis on geometry, right? Everything related to each other in the math. Otherwise, we cannot build the model, or we cannot represent the universe, or the physical law, or the electromagnetic law, or any other else that we can see or sense in our brain, right? Okay, and so if this is the notion, and then we should find out the A0, A1, A2, AN for a given signal. But the problem is that we have only measurement. For example, if we have any signal, and then we can take the what? This nomination in here based on the what? The function of the t, and so we can observe the what? The result of this signal, xt. We have for example, the t1 is equal to what? The x5, right? Or t at the 2.2, and then we can see the what? The x is equal to what? 2, okay? And so we can observe this just these things in here, and then we should model this function into the what? Into the infinite root system based on this nomination. And so we can use the what? Taylor expansion. How can we use that? This Taylor expansion is a function converting into the what? Infinite roots. And so if we have the any data which is given in the x, and so we can maybe drive the what? The x dot, the velocity value. Okay? This is why we can define this, or we should use the Taylor expansion in this form. But we have the different notion in here, because the Taylor expansion is given by this formula. We have the fx, which is equal to the what? The fa plus f derivative a 1 factorial times x minus a plus f double derivative 2 factorial times x minus a square plus blah blah blah. And so we have the final form just like this one, n is equal to the 0 to infinity value, f n order derivative in here, the basis of the a, and n factorial times x minus a n. This is the collection of these terms. And so if we have the any function, sinus, cosinus, or the exponential, and then we can generate, or we can translate the whole this function into the what? Infinite series of the what? The variable, which is in this case the x. Okay? And so we can relate the every function based on these nominations. Okay? But just see that we have the derivative rule in here, right? What's the meaning of this? We have used the derivative of these terms. Why? Why? Yes, it's the what? It's the dynamic form of these terms, right? Because it's the dependent of the x, okay? And so how we can find its dynamicity? And so we just take the what? The derivative, right? And so if we have the derivative, and so we can relate the at each function with the what? With this nomination, just like this one, right? And so if we have the x, and then we have the some coefficients in here, just like this one, f a 1 factorial, but the another term x dot is related to what? The f a 2 factorial, or we have the x dot dot in here for this function, and so we have 3 dot plus 3 factorial, right? And so each dynamic creates the another dynamic, and then if we model these things based on this information, and then we can model it, right? Because at each step we have add the one another root in here, just like this one, 3 2 3 4 5 6. But if we add the another root, and then we need to also add a one derivative term in here to model it. Okay? This is how we can expand any function based on the what? Based on this nomination. Just see that if we have the infinite roots, and so if we have the infinite number of dynamics based on what? The derivative, right? Do you understand that, guys?
Hocam burada türev alma işlemi bizim yeni eksenler oluşturmamızı mı?
Yes. Yes.
Yeni özellikler oluşturmamızı sağlıyor.
Yes. Because if we have taken a derivative term, and so we can define to the another dimension, just like the x dot, right? Because x is dependent on what? The x dot with the relation of the time. See that? If we have the velocity value of the 5, and so at each time we have the 5 meters, right? 5, 10, 15, 20, and blah, blah, blah. Okay? And so this independent from the x. Okay? And so in the Taylor expansion form, we can use it. Okay? But we have the some problem in here. For example, if we have this nomination in here, the example can be given in here, just like this one. Let's have a function like fx is equal to what? N 0 infinity cn x a n, right? This is the basic definition of the what? The general function notation, which is given in the slide 2, right? This is the identical with the what? With this nomination, okay? Just take the a is 0, and then we can see that in this nomination. And so we can add this nomination c0, c1 x minus a plus c2 x minus a square, blah, blah, blah. And so we have this function. And so how can we take the derivative of these terms? F comma x, or the derivative of the x. How can we do that? We can obtain the what? The c0 is going to 0, right? And c1 is coming in here, and so 2c2, right? And x minus a plus 3c3 times x minus a square, blah, blah, blah. Okay? In the first derivative. Okay? And so if we take the a value in here, it's the expanded form, or the pointing, the linearizing point at this time. And so we can say that this is the c1, right? And so the second derivative of this term is equal to what? The 2c2, right? And so it's also equal to the what? The a2. Because if we have these coefficients, and then we just take, or we can generate this function, right? And so if we take the first derivative, and then f derivative x is equal to the what? The fa. And so if I put the a value in here, and so this goes to 0, this goes to 0, and so we have the c1 value in here. And so this term is equal to what? The c1, right? This is simple. And so in the second derivative, we have the 2.c2. And so this 2.c2 is equals to the what? These terms, right? And so we can generate the whole the terms based on this expansion form. We can calculate it, right? And so in general form, we can write the Cn Fn a divided by n factorial, okay? So we can take or derive the whole the coefficients based on this information, okay? So but we have a problem in here. Problem statement in here, okay? In Taylor expansion, we have always used to the what? Different numbers, different coefficients. For example, at coefficients like the Cn is equal to the Fn a n factorial, okay? And so at each time this is different, okay? So this is a problem, because if we have, for example, it's the combination of this term just like this one, c0 c1 a, or these combinations in here, x a x minus a, blah, 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 blah. And so at each time we have the different coefficients. And also, if we take the derivative of this term, and so we have the c1, or in the second derivative of this term, we have C2, 2.C2. And so these coefficients always different, guys. This is a problem. But why? If we have the different coefficients at each time, we have the separate coefficients or the rate of the at each independent derivative term. For example, fx is equal to 1, 2x plus 3x squared, and so we don't have any general notion or any general capacity for for modeling these terms, because if we have the infinite root, and so we can select these coefficients 1, 2, 3, and then we can model anything. But at each time these coefficients are different. This is a problem. We cannot create the basis for this time. For example, if we have the fx, another function 2 plus 4x plus 3x squared, and so this is another model in here. This is a different coefficients, right? But how can we create the common mode or creating the basis part for these coefficients? Because these coefficients directly represents what are roots, right? And so we cannot define the common roots to define the model. But so what's your name? Hakan. What's your name? Mete. Hakan is a different person. Mete also is a different person than me, right? But two of them are human, right? And so they share the same roots or same coefficients to model it as a human. Okay? And so in order to provide this feature in the math is based on the what f(x), f derivative x, f derivative x must be equal to 0. Because in the Taylor expansion form, if we take the derivative, we have independent root for the dynamic, right? And so if we have derivative and then we create the x and x dot and x dot dot, or we can see this line x dot dot dot. But what if we take the derivative but always we get the same number? And so we can create the common point or part to represent the dynamic, right? At each derivation or at each derivative terms, and then if we take the derivative and the same number is going in here, and then we can create the dynamic in the one form with the basis form. How can we do that? Okay, and so just prove these terms in here, and then we have the problem in here. Fx is equal to the what? F0 plus F0 1 factorial x plus F2 derivative 2 factorial times x square, and blah blah blah. And so our aim is that we want to build this formation. Right? If we can do that, we just create the axis, independent axis, but with the same coefficients. And so we can evaluate all the axis as a one coefficients. One number. It's a transcendental number. In Turkish meaning, akıl üstü. Just like P. Right? And so how can we do that? The solution is simple, and the solution is coming from what? The Newton. Okay, suppose that we have B is a real number, and we can say that the fx is equal to the bx. We can write it, right? At each time we just use the x as a variable, but in this case we take the over part in here, which is the x. Just remember that if we have the, for example, x over 3, and so we have 3 roots, right? Or 5 and 5 roots for this number. But in this case, the variable is on the what? In the over part. And so we can define the what? The number of roots, changing this variable, right? X can be selected for what? 4, 6, 7, and so this is the dependent of the what? The x variable. And so we can increase the what? The number of the roots in here based on this information, or we can reduce it. Okay, we can set the whole the values. And after that, in order to provide this feature, and then we can use this nomination f x is equal to the what? Limit delta x going to 0 and fx plus delta x minus fx divided by fx, delta x, right? And so if you are writing this nomination and then bx delta x minus bx divided by delta x, okay? And so we can reorganize the whole the equation in here just like this one. Fx can be written by, we can take the what? The bx parentheses in here just like this one, bx, and so we can write the limit delta x goes to 0. We have this nomination bx1 delta x, right? And so at each differentiation or taking the derivative, and so this must be going to equal to the what? The bx, and so this part must be equal to the 1. Okay, yes. Okay. And so this must be equal to the what? 1. If we can use, or we can select the b in here just like this one, and then this bx always coming from in here, but this part must be equal to the 1. And so if we take the infinite derivative and then always produce the what? The bx in here, right? This must be equal to the 1. So if we're going to what? If we select this formation, the b is equal to the 1 plus delta x divided by delta x, and then if we put this equation, the b is coming from in here, and then we can write it just like this one, this limit converting into the what? The delta x 0, and I'm writing in here 1 delta x 1 divided by delta x times delta x, but the over, this is the over term in here, minus 1 is divided by delta x is equal to the what? The limit 1 delta x minus 1 delta x going to 0 produces the what? The 1, right? If we select the b just like this one, and so we can obtain the what? The 1. Okay, this is simple math. Just we are taking the what? The, in order to equalize this term as a 1, and so we can select this one, right? Because we have this formation in here delta x, and so this removes this part, and so we can take the what? The 1 plus delta x, and so we can remove this 1 term, and so we can always the 1. And so this form, or the b, is going to equal to this one, And so how can we evaluate this function in here? Therefore, we have b limit delta x going to 0, 1 plus delta x over, or if we return to the the infinite series in here, just like this one, limit n infinite value in here, just like this one, 1 over n, this one. Okay, because we are going to the 0 or we are going to infinity, and so this delta x can be written just like this one, 1 divided by n, right? And this 1 divided by delta x is writing as a n, right? And so Newton derived the binomial solution for this in order to calculate this limit values in here. Okay, and so 1 plus 1 divided by n is equal to the 1 plus n times 1 divided by n minus 1, 2, 1 divided by n square plus blah blah blah. This is the this is the expansion of the For example, if you are using the 2 in here, just like this one, taking the 2, and so 1 square, 1 divided by n square plus 1 times 1 n, or in the second root we have the 1 square, 1 divided by square, and 2n, just like this one. This is the binomial expansion, right? Just remember that. Do you know that x plus y square is equal to the x y square and xy? This is the binomial theorem. Okay, we can expand it, all the terms, as a coefficients of this one. And so Newton write these terms in here, and always we have the 1 divided by n over n. If we use this nomination, and then we just use this factorial form in here, just like this one. And so 1, this is the proof of this theorem, and 1 minus 1n, 1 minus 2n times 3 factorial blah 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 blah. And so at the end of this term we have this formation in here, but just remember that this is equal to the 1 because the n is infinite. 1, 1, and so we have always these coefficients. See? Okay, and so if we have this nomination, and then we can write it this limit value, n infinity 1 so n is equal to the 1 0 factorial, 1 1 factorial, 1 2 factorial, blah blah blah, and 1 n factorial, right? And also this is equal to the n 0 to infinity value 1 divided by n factorial, which is equal to the what? Which is equal to the what? Huh? No. This is the famous formula for the what? E number. This is the proof of the Euler number. If we are using the Euler number, just like this one, ax, and so it always produces at the differentiation to what? Himself or itself, right? And so if we have x function in here, ax, and so if we take the derivative, and always ex, and always ex, right? This is the proof of the Euler number. How we can utilize or how we can derive this E number? Because in the Taylor expansion we need a common values for the derivative operations. This is the proof of the E, Euler number. And so in the control theory, in the frequency domain, in the time domain, in every domain, we just use this E number with over X or over J or over something. Because, just say it. Yes, every derivation or every derivative operator yields itself. This is the common point or the basis for the what? For the dynamicity. But how we can reach this formation? In the functions, we have the many infinite roots, but we don't like it because at infinite roots we have different coefficients. But if I choose the E number, or if I use the E number, and then I can treat or I can apply the whole theorem based on this Euler number, because the derivative always yields to the what? To itself. This is a wonderful formula for what? For representing the infinite roots or infinite numbers, right? Or infinite models. Just remember that in your control theory lesson, we always generate this response as a natural response. E minus 5t, for example. Or in Laplace domain, we can take the whole derivative or the formation based on the E. Why? Because at each derivation or derivative terms, we can have the same coefficients. And so, this is not the time-dependent variable. Ex is independent of the variable. This is a transcendental number. Akıl üstü. Right? Because if you take the derivative of this term, it was always the Ex. And so it's independent of the time or independent of the variable. And so we can model anything in here. And so if you take the derivative of these terms, just like this one, Ex, always we have the unit matrix. This produces the what? The energy form of the unity. Or unit energy form at each derivation or each differentiation. Okay? And so we can model anything by using the what? E number. Independent of the what? The derivative operation. Okay? This is the proof of the E or Euler number. This is the foundation of the what? This Euler number 2.71 blah blah blah. Okay, this is transcendental number, just like the pi. Okay, any question? If there is no question, and we just take a break. Okay, and after that we will start at the 2.